Great. We now reach section 4.2, where we study the transform listener and how poses are saved into TF message types, but also how we can convert some of these TF types into geometry messages. So to compute frame transformations in our code, whether it's C++ or Python, we can use the TF library. Please check both of these links, especially the API code. So when we use a TF listener, this object is going to be looking into the TF topic. The TF listener object works as an independent thread and doesn't depend on spin or spin once. All information is extracted from the topic itself, and it then maintains a kinematic tree of the robot. The TF listener is able to transform data from any one frame into another frame. So you would provide it a base frame and a child frame, and it would provide you the transformation from the child to the base. This can be very useful for hand-eye coordination. So imagine that you have a humanoid robot or a robot arm, and you're going to get the pose of a target object. Now, first, you do that with respect to the camera, and then you do that with respect to the base. So here we have a chained transformation. So ultimately, we know the pose or the coordinates of the target object with respect to the base. The next thing we want to do is get the pose of the hand or the end effector with respect to the base. So that's our second vector. And finally, we can compute the difference between the target object and the hand. This difference then can be used to create a trajectory for the hand from its current position all the way out to the target object location. So in this section of the book, we're going to look at the example TF listener package, and we're going to look in at a few files of an example TF listener where we're going to be playing around with transformations across a few different frames of the mobile robot, namely base link, which is right on the floor in the middle of the mobile robot. And then we'll have link 1 and link 2, which correspond to the left wheel and the right wheel of the robot. In this package, we will have a demo TF listener class, which is composed of 3 files. The first one is example TF listener.h, which gives the class definition, example TF listener functions, where we have the actual implementation of the class methods. And finally, example TF listener.cpp, which contains the main function and where all the important function calls are taking place that illustrate the transformations. As a general overview of the main file, we're going to have a ROS headers, and then we're going to create transform objects. They're going to be one that goes base to link 2, another one that goes from base to link 1, and a third one from link 2 to link 1. After that, we're going to do the lookup transform on the TF topic and store the result locally. We'll do a printing to screen, and basically we're going to do this a number of times to show all the different transformations. Later on, we will also give an example of the computation for a chain transformation where we should get a result that we already anticipated from before. And finally, we'll also have an example of a failed transformation due to the wrong order of the multiplication in the chain. So this can help you understand more or less what we're trying to do here. So let's examine the main file. Here, the first thing we're going to look at creating the class instantiation. So let me open a terminal. Let's use ROS-ed to go over there. Example TF listener. Example TF listener.cpp. Great. So here we have the header file for the class that we include. We have our main file, we initialize, we have our node handle, a little bit of our ROS info declaration, and then right here we have the instantiation of our class demo.tf listener. Now I haven't really looked into this class yet, but I would like to ask you to look into the details as part of your homework. At any rate, we have this demo.tf listener object with a node handle passed as the input of the constructor. Okay? And immediately after that, we're going to create objects for stamped transforms. Remember that stamped here means that we're also saving the time at which a transformation took place. And we will also create objects for unstamped transformation objects. Now, so sometimes, like in this line, all of these objects are stamped transforms. We have 3 of them here. Base to link 2, base to link 1 to link 2, and then one that we're going to use for testing from base to link 2 using the chain multiplication. The ones down here are just transforms without the stamp part, where we're just interested in manipulating the pose. Okay? So looking back at this code, you can see that those lines are right here. Next, we are going to call the lookup transform method. This is part of the TF library here. And this method will take 3 input arguments. The base frame or the reference frame, it's a string, then a child frame, and finally the time at which we want to compute that transformation. Most of the time you'll be interested in providing the current time. That can be achieved by using the time class in ROS and passing a 0 for the input argument. Finally, we want to save that transformation. And here in this first example, we save that in STF base to link 1, which is a stamped transform that we used earlier. So we can see that that is done immediately right here. Now, since the let me see. This TF listener method is called through the dot operator, which in turn calls the lookup transform through the arrow operator. Okay. Once we have saved this stamped transform, what we want to do is then print the result to screen. We're going to use this method print stamped transform and pass that variable that we just computed. But looking into this method in the class is very interesting because we get to see how some of the API methods of the TF library are being used, getting the basis or getting the origin of that transformation in order for us to properly print results to screen. Okay? So here we might see out something and say, hey, here's the base to link 1 transformation, okay, which is what we computed right here, and we can take our class object and call print stamp TF. Okay, and then let's go back over here. Actually, let me go back one more time. Another thing that we can do is take again our class object and get TF from stamped TF. So here we pass the transformation with the stamp time, but just extract the pose, which is just this TF base to link 1. Okay, this might be used later in our code. So the other things that we're interested in doing is computing chain transformations. So we want to see how we might transform a frame from link 1 to link 2. And the question here is, how can stamped transforms be multiplied? Or what should the order of the parent and child frame be for both transforms? To this end, we use this method, multiply stamped transforms. This also will use API methods from the TF library, set basis, get basis, set origin, get origin, to extract information and do this step by step. As far as the class is concerned, we're just passing in here the base to link 1 transformation and then the link 1 to link 2 transformation in order to get the base to link 2 transformation. So please make sure you take some time to look into this method right here to see how these questions that I asked you are being addressed. Okay, that is going to appear a little bit lower in the code because for now we're just doing base link to link 1, link 1 to link 2, base link to link 2. And notice that here we're going to get this result, base link to link 2. We're going to get that transformation, but we want to get the same answer doing the chain multiplication. So that chain multiplication is going to be happening over here in this part of the code. So we would take these, we're going to do this in a number of ways. One is we can use just this multiplication operator, which is built into the TF library, and then we can just do these operations very conveniently in this way. So here we print out this result. Okay, we can then also run this function that I just introduced in the PPT, multiply stamp TFs. Now we're putting that in an if statement to see if this works out, because what this function is doing, it's going to be checking for the correct order of the transformations over here. If everything works out okay, we can just issue the result. But if they're not okay, then we might say something like attempt multiply of stamped transforms is in the wrong order. Okay. The other thing that might be interesting for us is extract the pose from a transformation. So here we just call this method get pose from transform, but this is a more interesting example. Okay, so this would be done in this part of our code. That extracted pose can be used in the following way. We can take that pose and add it to the child, which would be, or add it to a base link frame to see if we can get the target frame linked to. You see that? So here we're getting the pose of the transformation from link 1 to link 2. And then this can be added to, let me see, this is, added to the base link to see if we're getting the appropriate link here at link 2. Now let's run this code quickly by running these commands and see what that might look like. Okay, let me close this window and subdivide this. So at the very bottom, we're going to start Gazebo, ROS launch, Gazebo ROS. We're going to do an empty world. Here our Gazebo simulator will start running. Okay. The next thing is we want to ROS launch the Mobot URDF package with the Mobot with ARM and joint publication .launch. So here we have all the joint state information. We also want to run the robot state publisher, ROS run robot state publisher, that will help us to incorporate joint state information into TF. Okay. And then finally here, we're going to run the TF listener. Let me do that again. ROS run, example TF listener, example TF listener. And it throws out this result. Let's take a quick look at what's happening here. At the very beginning, we get A, we're in main, we're instantiating an object of type demo_tf_listener. Now we're in the constructor, and then it says waiting for TF between link2 and base link. So we're doing the lookup transform, but then we get a warning saying the target frame does not exist. And the reason this occurs is because we need to be listening to TF for a certain amount of time before we get all that information. TF is a large topic, and we need to traverse it in order to obtain the information. So we get those warnings, and then finally, when all the information has come in, as we attempt to continue to look at the lookup transformation, we can say TF is good. After that, we print all the information we looked at, our code. From base to link 1, our frame ID or our reference frame is the base link. The child frame ID is going to be link 1. And then the vector from the reference frame to the child frame is going to be this one right here. Okay, negative 27 centimeters in the x direction, 0 in the y, and 55 in the z direction. And for the orientation, here there's no change in orientation. Then by going from link 1 to link 2, the vector from the reference frame to the child frame is 0, 0, 1. So just a difference in the z direction, and then this orientation vector right here. Now the orientation vectors are a little bit easier to understand. For example, the one we had before, this first column represents change in angle about the x vector. If we have a 1, 0, 0, it means the x vector of the reference frame and the x vector of the child frame are pointing in the same direction. If we have a 0, 1, 0 on the second column, it means that the y-axis of the frame, of the reference frame and the child frame are pointing in the same direction. If we get a 0, 0, 1 on the third column, it means that the z-axis of the reference frame and the child frame are pointing in the same direction. So here we have the same orientation. On this one right here, it's slightly modified for the x. We have 0.98, 0, negative 0.15. On the second one, it's a little bit harder to see, but it's 0, 1, 0, so the y-axis is the same, and then the z changed a little bit. So there's been a rotation about the y-axis. We're almost pointing in the same direction, but both x and z have changed slightly. Yes. And so we get the same thing. Now this is base to link 2. This is our vector. Okay, and this one, where it's going to be interesting for us because immediately right after that, we're going to use this for the chain transformation. When we extract the TF from the stamp TF, we see we get exactly the same pose and the same orientation vector. And then here's the result of the multiplication from base to link 1 and link 1 to link 2. You can see that this result is exactly the same as this one. It makes sense. When we go from base to link 2, we should get the same thing compared to going from base to link 1 and link 1 to link 2. The orientation matrix is the same, or the rotation matrix is the same right here. And we did this in two different ways, using the multiplication operator and using our method. And so both result in the same work. And then there was one attempt where the order is wrong. So here we say we cannot do that. And finally, this is the example where we're extracting the pose of link 2 with respect to link 1. Okay, and this is the pose and the quaternion. We can use that pose then to add it to the base link, and then we are going to get these numbers, which is exactly the transformation again that we had over here. going from base to link 2. So this was a quick review, but please take some time to walk through the code, think through the concepts, and make sure you understand how the transformations are working. So this is repeating what I just presented. Okay, these are all the results. One more way of analyzing the transformations is by using a command line tool called tf-echo coming from the tf package. Here we can use run to run this node tf-echo of the tf package, and what we can do is provide a base reference frame like base link and the child frame like link 1 to examine what that transformation might be. So we get those results. Let's go to base to link 1 right here. I'll open a new window, place it on this side, and say run tf-echo base link to link 1. And after a little bit of time, it's able to pick up that transformation. And you can see that it's stagnant, it's not moving, and we get exactly the same numbers as we have over here in our terminal. And we also get the rotation information as a quaternion, RPY in radians, and RPY in degrees. Here, there is no change, so the identity quaternion is this 001, which is equal to the identity matrix and the rotation matrix over here. So this is a very useful tool, and we can simply enter any two existing frames and then obtain the information. Okay. A few other considerations. When we're using the lookup transform, it's possible for us to get an exception when the frames that we have input into our method are not found. So in order to avoid this, it's very important to use a try-catch block. I can quickly show you this where we're looking at the constructor of the demo TF listener class. Okay, so for example, set example TF listener, example TF listener functions.cpp. And so right here in this constructor, we will see that we're going to have a while loop. This while loop is going to run continuously until the lookup transform has returned a true value. So here TF error is originally set to true just to enter the while loop initially. It's immediately changed to false. Here we have our try catch block. Within the try block we have this TF listener lookup transform that we want to attempt. Okay, and if there is an exception from the TF transform, we can use this TF transform exception type and then be able to catch it here and issue a warning saying, hey, we need to retry. TF error is changed to true again, and there's some sleep going on here. We call spin once to attract new information, and then the while loop is reissued again. So this construct right here is very important in order to successfully call lookup transform, especially when there's a possibility of running into an exception, which may happen at the beginning of the call when we're doing a first pass through the TF topic. Another small note is if you're using multiple computers, and this is possible in Rust, all of them will have the same ROS master, but not all the computers have the same clock. So this clock is important in order to keep the timestamps of a transform listener, event topics together. So when we're using different computers, we will not get the same timestamps unless we synchronize the clocks across computers. To do that, you can install this program called Crony to resolve synchronization problems. The last thing, and a place where we'll pay a little bit more attention, is how to extract information from TF types and place them into geometry messages. Geometry messages are going to be, geometry messages post-stamped is going to be a very native ROS type that we can use extensively in our code to do different kinds of manipulations, including kinematics and so forth. So there's an interest of being able to go from TF stamp transform information to geometry messages post-stamp types. So here we're going to look at the example TF listener functions, a file, and we're going to go into the get pose from transform method and look at that in detail. Okay? And the logic goes a little bit like this. Let's extract the quaternion element from the TF type. And how do we do that? Well, we're going to create both a TF quaternion type and a geometry messages quaternion type. And then what we had originally in the TF is going to get stored here in this TF quaternion object that we created. And then individually save each part of that quaternion, the X, the Y, the Z, and the W elements of the TF quat, and then store them in the corresponding elements of the geometry messages quaternion object that we created. The same logic follows for the pose. We extract the pose from TF in the following way. We create a TF vector 3, and we also create a geometry messages point type. From that vector 3, we copy the pose of the TF object into the vector 3, and then save each of the XYZ elements in vector 3 to the corresponding point types. So at the end, we have this geometry messages quaternion, and we also have this geometry messages point, and then both of those can be stored in a larger structure where the pose is retrieved, and there are quaternion and pose portions to it. Okay, so let's look at that code to get an idea of that. So we're down here and get pose from transform. Okay, so this is the method that we are looking at, roughly speaking. Let me go down a little bit more here, and then up a second. Okay. So we are going to take a stamp transform as our input, that is TF stamp transform, and we'll call that STF. And we're going to construct a transform using elements of STF. So here what we want is just a transform element. We're going to call that TF. There's no timestamp here. So the get basis will return the quaternion, and the get origin will return the position. Oh, I'm sorry. I'm in the wrong function. We still have our stamp transform here. I apologize for that. But we have geometry messages post stamped type here, st pose. So this pose has the position and the orientation, and at the end we're going to fill that out. Okay, we also have this geometry messages quaternion quat, and we have this TF quaternion TF quat. I think if I just separated this in this way, I think it would make more sense. We're going to use this at the very end, and these two we're going to use immediately. So we have the geometry messages object for the quaternion, and we have the TF object for the quaternion. This TF quat will get this TF object and extract the rotation into it. So at that point, this TF quad has the quaternion in it. The object from the TF library allows us to extract each of the individual members. So we can say, give me the X element of TF quad. And then we want to save that into the geometry messages quaternion. Now this also gives us access to individual elements of the quaternion, and we can just use the dot operator. So we can say quad.x equals TF quad.x parentheses. We do that for the X, the Y, the Z, and the W. And so all information is now saved in this geometry messages quaternion object. Once we have that, we can take our stpose here, access the pose part of the structure, and then the orientation part of the structure, and save that to it. Immediately, we'll do the same logic for the position. We create a TF vector 3 object and a geometry messages point object. We extract the origin information, or the position vector, from our TF input variable and save it into this vector 3 TF object, TF-vec. We can also get the individual elements, calling these methods, get XYZ, and save them into the XYZ elements of point. Once we have done that, we can then save that point to the stpose post position part of that structure. There's one last thing that we want to do, and that is to save the frame ID. So we can access the stpose header portion and save the TF frame ID in this way. Similarly, for the stamp, we take the stamp at which that transformation took place and save it also in the header.stamp portion of the geometry message post. And then finally, we can just return the stpose portion of this method. Okay, so that sums it for section 4.2. That gave us some intuition about the lookup transform and how we might then also interact with the conversion from TF types to geometry messages types. Thank you.